So my presentation is about agri-food drones application using robotic operating system. I have presented myself already in the beginning of this presentation. So my name is João Valente. I am assistant professor in the information technology group. I'm also the head of the social drones lab. And I will make a presentation where I will show you some of the real applications we are using robotic operating system. This presentation is going to be organized in 4 models. So I'm going to talk about applications drone oriented, then simulations, then water drones, and then a little bit work in progress that we are doing, also drone related. Let's say that I will introduce it to you, the father of the drones, to say something. So a little bit about myself and about a little bit of the context where I work. So as I know, I work in Wageningen University and research. We are in Netherlands. We are in the province of Gelderland. As you know, Wageningen is a top university in agriculture and forestry for several years in a row. Also, top university in Netherlands for several years in a row. We are very proud of that. So it's always something that I would like to enhance. Then you can see here a little bit a map with lots of arrows. This was a little bit where I move since I am a researcher. So I born in Portugal. And I did my bachelor in computer science and electronics engineer in the new University of Lisbon, my master in La Sapienza University of Rome. Then I moved to Madrid. From Madrid, as a PhD, I've been visiting labs in the United States and in Brussels. And then I was assistant professor in Madrid, and after all, I moved to Wageningen University. I was a postdoc, then lecture, and then and currently I'm assistant professor. So let's start with the drones. So one of the applications that we are working, and that actually were already introduced by Omar, is that we are working on food safety, where we are interested in keeping track of the health of the plant, and this can be also spotting the disease, keeping track of particulate matter after a fire. For instance, there are several particles that go around, this going over the crops, and then of course we are going to eat all of that, and it's not good to our health. So we are using these drones equipped with advanced sensor technology, cameras, electronic noses, and to sense all the environment. How we used ROS in this? So we are using for this application, we have been using the DJI Matrix 100, which is quite handy because it was one of the first drones with ROS support. And this is quite important because it was when we could start using the DJI drones autonomous and program our own behaviors. So here you can see, you can find this information, of course, in the robotic operating system webpage. You see that this is the package that we are using, supported by DJI. You can see that right now you have support to the Matrix 100, 600, and 210. But also recently, you know, there is another new drone. There is also support for it. We are going there later. This is the configuration that we have. Also, I think Omar has already given some ideas about it. So we wanted to use drone on board the M100. What we use is that in this case, we are not using a very advanced board. We are using the Raspberry Pi 3, and it makes the job. So we have ROS running there. We can read all the telemetry of the drone on real time. And then we have on the right here this nice sensor nest with tons of electrochemical sensors that they are also sending information to the base station. And now, of course, you are asking why we don't read also the sensor payload directly from the Raspberry. The point is a little bit that the manufacturer who designed this system has just habilitated this, let's say, this channel. So what we have here is that we can read both all the telemetry from the DJI 100, M100 on board, and we can also send it to the base station, of course. And here we have just, we can also receive the information from the sensor array, and we are reading here directly also using host serial, because this communication is, let's say, a serial LoRa communication. So here we have a device which we connect through serial. We can read everything. We did a host package that reads all the data from all the sensors. And here again, we are going we can also receive all the information from the telemetry of the drone. And then in real time, this is the kind of visualization that we have. We can have this high definition of the gas dispersions over a site. More things. So another nice application is indoor flying in greenhouses. So using drones assistance for plant phenotyping. This is a quite recent work that we are still working on and investigating how actually we can have these autonomous drones on the greenhouse for monitoring plants to derive phenotypes and to assist researchers, practitioners, and etc. Which kind of research we are conducting on that? So of course, for us, again, targeting platforms which we can use ROS and we can program using robotic operating system. And to make a balance between availability, price, and robustness. So we have decided we first started by investigating with the IR drone from Parrot company, and recently we're also doing lots of work with Anafi. Both platforms have a software development kit. The IR drone has already a very nice interface for robotic operating system, as you can see from the previous presentations. There is support, integration in MATLAB, Simulink, Gazebo. So of course, this is a well-known platform from the community. And now, of course, Anafi is a more recent platform. There is a software development kit. It's possible to program it using Python, but still the link with ROS is still not 100% clear and working. But there are, of course, it's not direct, but there are workarounds. Again, here we have been for working with IR drone. You can use the tool simulator, but also all the tools that my colleagues previously presented. And of course, for directly manage to program the drone, you can use IR drone autonomy. First of all, one of the important things, of course, one thing is, okay, I have a drone, I have robotic operating system, I can do whatever I want. Of course, that is never the case. There is so much work until you can get the work flying autonomously. For instance, for us, one of the biggest challenges that we have faced in the greenhouses was kind of this effect that we have inside of the greenhouses. For communication that attenuate a lot the communication of the drone. So let's have in mind these platforms are commercially available, are quite handy. We can program it using robotic operating system. There are lots of things that can be investigated and we can advance with lots of research, but at the same time, they have their own limitations. And one of the limitations is actually the antennas that they have on board. Furthermore, these in an environment where you have so much infrastructure, metal infrastructure, cables, and other electromechanical devices, can be a problem because, of course, we are making all the processment in the base station, not on board. And that means, of course, that if we want that the platform flies autonomously using, for instance, visual SLAM, we need to make sure that there is a very, very good communication. So one of the work, the research that we are doing is trying to understand how to manage this signal propagation, how to define what is the maximum flight range inside of the greenhouse, etc., etc., etc. Another application that it's quite important for us at Wageningen, and that we have already lots of experiences in yield estimation. And for this application, what we are using is currently the M210. Again, fortunately, it's a nice platform that can be programmed using robotic operating system. We are using deep learning for detecting the amount of apples in the trees in real time. There was an exhaustive work of labeling did on the trees that we use the CVAT software. You can find it quite handy online. You can share between users, what is beautiful because you need tons of people to doing this sort of work. Tons and tons of images were labeled. You need tons and tons of image to achieve the result that you can see here on the right, that are preliminary results using real-time detection using MOTS. That is quite a recent approach. Again, for this right now, of course, we don't have yet this onboard the platform. That is the step that we are going to give now, but we have all this methodology already set up. And once we have this more accurate, is going to be programmed in this platform. So we are going to pick this model, put on the platform, and by using this DJI SDK that has support on ROS, we are going to try to have this in real time. Another nice application, livestock monitoring. Here we can see already a very nice demo where we are mapping the corridor between the wall of the barn and the cows. This is quite important for also monitoring the health of the animals inside of the barn. And this is incredible what we are doing this with this beautiful and small new platform from DJI, the DJI Telio. I mean, if we use the WL in Spanish, but let's say that this is a DJI Telio. And again, this platform has support in robotic operating system. In this case, we are using the package Flock, called Flock, which works very well under ROS. There is another package that you can use in ROS 2 if you want to give that step to the new version of ROS. And for visual simultaneous localization and mapping, we are using this package ORB SLUM3. Let's now jump on the simulation, and you are going to understand why simulation. So one of the most important things for a farmer is actually understand what is the right time for harvesting. This is quite a challenging and involves tons of work, daily work, because the farmers need to scout the orchards on foot, of course. And if you are talking about 1 hectare is a lot, 10 is a little bit more, and imagine what is 100. So this is tons of work, time consuming, not accurate, and of course it's an activity, it's a cultural practice that has been doing for years and years, and what we want is to change the way this is done, because now we can do it using drones. So here We have been studying how actually understand what is exactly the best day for harvesting using drones equipped with vision sensors, machine vision, and machine of action. Of course, because the state of the art for what the electronic news concern is not very advanced, we needed to go to simulation and try to have more understanding what are the best spots for sampling, what is the effect of the drone what is the effect of the drone in the gas dispersion, etc. And for that we have used GADAN. So GADAN is a gas simulation framework that can be used to simulate gases in general and can be used to advance more on research. Here, of course, there is support with robotic operating system. This is a small video presenting GADAN. Of course, this video is not, the credits is from the University of Malaga and Örebro University in Sweden. You can see it online. Let's see if I can change it. Yes, and how we did that? Because of course, GADAN is being used to have gas sources around the building, to test different kind of robots, but it was never used for outdoor applications and applied to agriculture. So what we actually did is that we have modeled a true orchard, a physical orchard. We have picked all the physical components of an orchard, as you can see here on the left. We have modeled exactly the number of trees in the area that we have. We have used wind dynamic models and dispersion models from the rotors from the drone, and we did tons of simulations to understand all of these questions about how is the best spots to use the system, how we can use the system if there are different kinds of wind speeds. So what is the effect? And there is enough measurement, which extent we can use drones for that. So all these questions we have already somehow answered. And there is a recent publication about this that is going to pop up at any time. We are actually expecting it. If it's not today, tomorrow is going to be online, and you can understand more about this experiment that we did. Another nice application that is still in a very early stage is using touch. So we want to give another step. Because again, these cultural practices that are done by the farmers need to be changed to a more autonomous way and automatic way. So one of the activities that consumes tons of time is the visual inspection at the tree level, but actually the activities that the application expert needs to apply to each trees. So here, one of these applications, for instance, tining. When it comes to spring, the trees are full of flowers and the farmer needs to get a perfect balance of flowers and then needs to apply or chemical tining or mechanical tining or hand tining. And in this case, what we want is to do this in a more sustainable way using drones with grippers that can do this work for the farmers. So we have developed different kind of grippers and we are now testing it in a drone to see how possible this is. Now from air, let's go to the water, because there is always room for water drones. One nice application that is also that we are also researching on is for fishery habitat mapping, applied to the fishery industry. So there are several different applications here. We have built our custom boat, our custom water drone. There is a first model that was built back to 2017 when I was assistant professor in Spain. Now at Wageningen, we are building the second version with a better navigation with better navigation configuration, upgrading the algorithms, upgrading all the electromechanical structure, everything, and also add more intelligence to this water drone. So we have several sensors: pH, cameras, turbidity. Not to talk about the navigation sensors, GPS, IMU, sonar, perhaps in the future laser scanner. So this is equipped with all this instrumentation. It's a water drone, a remote sensing platform for inland water environment, but at the same time is also can work in collaboration to other robotic platforms, in this case to other water drones or aerial drones. In this case, we see here that is land on the top aerial drone. And for this is very important robotic operating system, because of course we need to have a solid and a robust infrastructure of communication between the platforms so they can communicate and collaboratively achieve a determined task. With tasks they can achieve collaboratively, very simple. For instance, one application is, for instance, the water drone looking for estimate the fish biomass, and at the same time you have the drone that looks for fish biomass, and you have the water drone that can expect a determinate zone with more precision. Another application that we are also investigating on is looking for furtive fishery, so etc. There are many applications for what the fishery industry concerns. The last application, I'm going to show this video, although it's online. I present you, ladies and gentlemen, the cyborg farmer. So the cyborg farmer, as you can see, the cyborg farmer, half man, half machine, all the core done in robotic operating system, and is a new idea, a new concept, how to, again, to monitor agricultural sites, but also at the same time, how to make humans and machines to collaborate on the field. So this is a little bit in base with background of my research line, how to bridge this gap between flying machines and farmers, how to make this technology to make them more closely. And we can see here, this is just, I'm not going to enter in details on the architecture, but of course you can see that this is 100% robotic operating system, custom built. We are using 3 cameras, Raspberry Pis, other sensors, IMU, GPS. And of course you can see that you have lots of host topics that publish the image of the cameras, of course, all the telemetry from the cyborg farmer. And also we can see some publishers, because the idea is that, of course, what we want is to mimic the human being cognition and make a digital twin of that and build it inside of the mind of a aerial drone or a water drone or whatever. So this is also how you can see, this is another application of how the position and the IMU of the position of the cyborg farmer was combined in such a way to have a very, very accurate position on the field. Here we can see this is just a visualization of Revit, and I did not wrote, and the navigation stack of robotic operating system that is very common to use it on ground robots. We have applied here to the cyborg farmer. And finally but not least, of course, I have a couple of more slides, but what I just want to say is that I want to share these credits with all my students, all the people that is working with me. So this is not only my credits, but the credits of all of the people that make part of the Social Artificial Intelligence Drones Lab, which mission is to design human-like drones, bridge the gap between humankind and drones, and in general, develop drones for good. Currently in this lab, we have myself, one postdoc, 5 PhD students, 16 master students, and 2 bachelor students. And I hope that I did not forget nobody. And we have several toys, parrots, DJI drones, a custom built drone, etc. If you want to learn more about drones, please register in our online course, in our MOOC. That was a nice initiative done with my colleague Lamer Kostra. We have one MOOC online with 3 modules. You can get a certificate, and moreover, the Dutch students can also have SATSs, because we have bring this MOOC to our study program. And so there is also the possibility that you get this course in your curricula. You will have always in your curriculum, but let's say in your academic portfolio. We are very happy also to announce that we have started to sketch MOOCs Drones on Agriculture 2, that hopefully is going to be launched in 2021. And finally, you can find more information about myself and the drones and the Social Drones Lab in the social media, webpage, Instagram, LinkedIn. You can also check our publications on my Google Scholar. You can follow us on the Social Drones Lab in Twitter. And of course, you are very welcome to drop an email whenever you want. Thank you very much for your time. Thank you very much for listening to me. And please let me know if you have any questions.